Good afternoon and welcome to this afternoon devoted to the seismic assessment strategies for masonry structures. S.T.A and Tremuri are proud to present you a panel of distinguished professors and engineers from all over Europe. I would like to thank them all for having wanted to share today with us their interesting lectures and case studies. A special thank you to Professor Rita Bento, University of Lisbon, and a more than warm welcome and thank you to Alessandro Marasca, Hopper Engineering, the Netherlands, Alexandre Costa, NCR EP, Portugal, Tsiamtsiakiris, Ergocad, Greece, Henning Kirmse, KPPK, Austria, Romina Sisti, University of Naples, Federico II. I would like also to mention our distributors who have worked with us side by side to let you all be today. Ingwer for Switzerland and Austria, Technosoft for the Netherlands, Edisti, Slovenia, Croatia and Serbia, Ergocad for Greece and Cyprus, Anashimoes, Portugal. But the greatest thank you goes to Professor Andrea Penna, University of Pavia, who accepted to be the chairman and key speaker for this event. I hand over to you, Andrea, and again, thank you all for being here with us today. Enjoy.
So thank you all. Thank you, Simonetta, for your kind words. And in particular, I thank you all the almost 300 participants to this online event that I think is a sign of the high impact and the high interest that these topics that we are discussing today and the very interesting presentation that will be given by a distinguished speakers that Simonetta Verdi was mentioning in her introduction will be say the topics and the new features, the interesting case studies that will be presented by all the presenters. I will say leave now allow 5 minutes for short video presentation that will introduce the S.T.A background, the Tremuri background, and the say present and future of these activities, please.
S.T.A Data was founded in 1983 by Adriano Castagnone, civil and structural engineer since 1978, and pioneer of scientific software for structural engineering. The company was born to provide civil engineering services and consulting. We have always had a particular interest in the evolving sector of IT, foreseeing the enormous opportunity of applying it in design and computation. Before focusing on software development, S.T.A Data realized important projects both with private and state-owned companies. That's our strength, because beside IT experts, we are professional in structural design. The company is currently composed by 15 employees and several consultants, all highly professional qualified. Thanks to the continuous development of work and collaboration with the university and professional world, it is always able to offer advanced and constant updates to its customers. Application S.T.A data allows you to face everyday work with simplicity and effectiveness. The company goal does not end with the search of new IT solutions. The offer of S.T.A data includes support, training, and consulting services, including individual projects, so that the professionals are immediately operational. Thanks to the technical expertise and the state-of-the-art solution, S.T.A data is a solution to the real problems of designers. Tremuri is the masonry structures analysis specialized software. It is the leader in the world. It is used for existing and new buildings. The software performs nonlinear pushover analysis. The mesh is made with the FME method, frame by macro element, specially studied for masonry structures to better represent the behavior of masonry structures. Now the software it is available in Italian, Greek, English, German, French, and Albanian, and performs analysis according with Eurocode 6, Eurocode 8, Italian National Code, Switzerland National Code, and the Netherlands National Codes. Tremuri takes origin from Professor Lagomarsino's academy research, and actually it is used for this purpose in more than 80 universities. Engineers and companies that use Tremuris for professional purpose are widespread in more than 30 countries. Now let's go through the modeling inside Tremuri. One of the most important characteristics of Tremuri is that it is possible to model floors with their real stiffness. As you can see in the picture, this allows you to take into account the correct distribution of the seismic forces on the walls. Into Tremuri are available a library of walls and floors, and in this way you can easily model this kind of elements. These are the walls that are available in Tremuri. And even if the majority of the floors can be modeled with this library, into Tremuri it's always possible to define directly all the parameters of a floor in order to create your own definition and the real stiffness of the real floor you have in the structure. Moving to the vertical elements, several structural objects can be modeled in Tremuri, like single masonry wall or reinforced concrete walls, columns and beams, and a combination of walls with beams and tie rods. Into a wall can be modeled different materials, different elements, and then they can also have the function of reinforcing the current wall. To reinforce walls into Tremuri, you can easily also model reinforced masonry, reinforcement with FRP and FRCM. The mesh inside Tremuri is specialized for masonry structures and is made with a frame by macro elements method. This method has been studied for the masonry structures to better represent the behavior of a structure made with the main structure in masonry. Using this method, thanks to the automatic mesh performed by the software, then the engineer can easily pass from the reality to the model, taking into account all the significant aspects of the structure.
Okay, thank you. I think we have all to thank S.T.A for hosting these and organizing this event, and for this clear contribution they gave to the spread of this software and of these tools. I think that I personally have to thank S.T.A because when we started this Tremuri project, Tremuri was born in the university, as it was mentioned in the video, and it was something that we were working in during my PhD and some previous works, and then many work which was done afterwards. And we did this in in a very, let's say, naive way, as in many conditions, in many situations we do when we work in a university. It was very spontaneous. Then, with the help of S.T.A, it was possible to transform these, I would say, brilliant research into something that was transformed into a everyday tool for engineering practice. I think that given these this word that everybody knows, I think that we can start with this event, the first presentation, which is a contribution by Professor Rita Bento. Rita Bento is a professor associate professor at the Istituto Superior Técnico di Lisbon, a university in Lisbon. She is a famous expert in earthquake engineering, and she is very well known in Portugal, but not only in Portugal. I think that we can then now start with the contribution, recorded contribution by Professor Bento.
So good afternoon to all. First of all, I'd like to thank S.T.A, the organizers, for having invited me. It's truly a pleasure to be asked to deliver a speech on this international webinar. So I'm here today to talk about the seismic assessment of the National Palace of Sintra, a study developed from 2018 to 2020, where Tremuri program was the primary software we used. So let's start by talking a little bit about the palace itself with this slide. So the palace dates from the 11th century, and it was labeled as a national monument in 1910, and it's part of Sintra's cultural heritage inserted by UNESCO in the World Heritage in 1995. As you can see from the slide, it's a very complex heritage building. It is composed of different reinforced masonry buildings, various intermediate levels, rooms separated by some steps, and the whole space has a layout that somehow it reflects the topography of the place, because it was built against rock all over the different buildings. The number of floors varies from 1 to 6. You have taller buildings and very small ones, and all the buildings have varying perimeter walls of rubble stone masonry, and the type of masonry varies from building to building, and even the same building, it varies from story to story. The rubble stone masonry presents different types of stones and dimensions, up to 30 to 40 centimeters long, and a various type of airline mortar. The thickness of the perimeter walls of the ground floor, just for you to have an idea, varies from 0.35 meter to 2.2 meters, so significant difference of thickness of the walls. In order to perform a complete seismic assessment of the palace, a multidisciplinary approach was followed with a multidisciplinary team. A historical approach was performed and a visual structural in situ survey. In fact, a significant in situ surveys have been done. This just before to proceed with the experimental campaign. And for the experimental campaign, we have started with a geometric survey with a laser scanner and a Falcon 8 Plus drone. We have performed ground penetration radar surveys, sample collection for the masonry, flat check tests, and ambient vibration tests. From the cloud points obtained with laser scanner and the drone, a 3D BIM model was developed in Revit, which includes, beyond the geometry, obviously, attributed data of various types assigned to each of the elements of the BIM model. So we have included in the final model historical documentation, description of materials, construction stages, information from experimental in situ tests, and even the main outcomes from the seismic assessment analysis that you have performed in all the palace. In this slide, you have only one wing of the palace, the manual in building, and a CAD and the 3D model represent on the right side of the slide. So from the laser scanner of the outer and inner parts surfaces of the palace, it has been possible to obtain an incredible 3D definition of the geometry of the structure. And to illustrate this, just some results of these outcomes. So what we have is the complete geometry of the two massive conic chimneys that you have in the palace, the possibility to be sure about the thickness of some walls which connect different parts of the palace, just to illustrate the chapel and the kitchen, where the width vary completely along the length of the wall, or to detect some curves walls that it was impossible to get it from another surveys without using laser scanning. Or even, as you can see from this image, the possibility to get very careful and very precisely the geometry of the roofing structures, which consist mainly of timber truss of different types, so all over the palace, with the exception of the kitchen. All the buildings have timber trusses for roof. And I'm completely sure that obtaining the correct geometry is crucial for the calibration of numerical models and for the adequate seismic assessment and seismic performance of this type of structures. Thus, for this type of complex masonry buildings, I think this is the correct way to get the geometric properties of the structures. As far as the GPR survey is concerned, we have performed these tests not only in the some of the walls where you have removed some samples, but also in all the pavements with vaults, just to be sure if they are in fill or not. And in some walls that were built against the rock, just to be sure how was the connection between the wall and the soil and the rock. We have used different frequency antennas, and with these we're able to get some important information and to be allowed to discover some construction techniques, some types of materials, anomalies like the presence of voids, cracks, or even water. For the characterization of masonry, we start with some stamps collection, so it's a qualitative characterization, of course. The location was chosen on the main structural walls that characterize the principal periods of construction of the palace, of course being aware of the countless limitations that we have in a palace, because of the existence of tiles, of painting, so it's rather tricky to choose the place to get these samples of masonry. The flat checks were carried out preferably in the same walls where you have removed the samples of masonry, if not possible in the same wall, in very close walls of the walls that you have removed the samples of masonry. And the objective was to characterize the mechanical properties of masonry. It is worth mentioning that the inspection windows that we obtained before to carry out the flat check tests allow us to proceed to the masonry qualitative evaluation. So it was really very important for the qualitative evaluation of the masonry. The flat checks were done with 25 centimeter depth, the size of the flat check. We have here an image of flat checks used. So the results obtained with these tests were considered with caution, because you have very thick walls and you are testing just the external part of the walls. We have performed single and double flat check tests, and with these we estimate the actual state of stress in the masonry, and of course its strength and stiffness. A campaign of ambient vibration tests were performed in the sum of the palace bodies, chosen for their structural importance, existence of damage, and history. These tests allow to identify the dynamic characteristics or dynamic properties, frequencies and mode of vibrations, which in turn were crucial for the numerical calibration of the models. The locations of the experimental in situ tests were represented in the beam model. So you have here the plan view of the Manuelin building, and the main results obtained linked to the model or added to it as attributes. So we have here some images of the Manuelin building and the tests that you have performed in this building. This film shows how the information related to the masonry samples, flat check tests, and the ambient vibration tests have been inserted linked to the beam model. We have the identification of the areas where the masonry samples were removed, where the tests of flat checks were carried out, including some photos and the main results reached. So for instance, for the ambient vibration tests, location of the sensors and the modes of vibration have been considered and included in the beam model. In the beam model, it was identify all the floors and walls where the GPR tests have been performed, and it was really important and main results as well. As you can see here, linked to the beam model, the report with the main results of these GPR tests. The mechanical characterization of the materials defined after the realization of the experimental campaign and after the calibration of all the numerical models were also linked to the beam model. And here you can see for the same building, Manuelin building, all the types of masonry and materials that you have considered in the model, as well as the properties that you need to perform the nonlinear analysis of the global model with the Tremuri program. So let's move now to the definition of the seismic assessment itself and numerical modeling of the palace. The definition of an effective nonlinear model for the seismic analysis of masonry structural elements represents crucial steps, as you know, towards a proper seismic assessment of existing masonry building structures. For the seismic assessment of the palace, you have considered the in-plane and out-of-plane responses of the masonry, and you have performed nonlinear analysis. Considering the size and complexity of the palace under study, where this figure is really illustrating the complexity of the palace, I do believe that the macro modeling approach is the tool applicable to large scale computations. Thus, in this study, the seismic behavior was assessed by performing nonlinear analysis through the Tremuri program. The Sintra National Palace, as I have already mentioned, is characterized by aggregation of bodies, quite clear in this image, intensely affected by their dynamic interaction due to the shared boundary conditions. You have all the buildings sharing by each other with some boundary walls. the structural model, of course, needs to consider the effects of those interactions. At the beginning of our study, a unique global model of the whole palace in the Tremuri program started to be developed, but due to the structural complexity, dimension of the palace, developing a unique model proved at that time to be computational demanding, and we got significant convergence problems, and it was almost impossible to calibrate our model based on the experimental results with a unique model. So we decided to give up. In the right side of the slide, you can see the model when it was decided to stop the development of a unique model of the palace. Therefore, separate models were developed, calibrated, considering all the time the effect of the adjacent buildings and take into account the field survey and results of the experimental campaign. Mainly the ambient vibration tests. They were crucial for the calibration of the different numerical models. So this, we have the identification of all the bodies that you consider in this study with the designation of the names that we gave for all the bodies. I have to say that among all these units, the unit 1, the Manuelino building, and the 10, which correspond to the kitchen with these two high chimneys, were the most challenging ones, I have to say, and these were due to different reasons. So if you move to the Manuelino building, I have to say that this challenging was mainly due to the dimension of the building, irregularity in plan and in height, different levels, walls without continuity in height. So this was mainly the main reasons why it was so difficult to reach the final model of this wing of the palace. For the kitchen, the unit 10, this is mainly due to the presence, of course, of the two massive chimneys with a conic configuration. In this case, we have used different softwares. We start with SAP 2000, and the main reason was trying to have a preliminary outcome, a preliminary dynamic characterization of the building and of the chimneys, because this was rather important to perform the ambient vibration tests and to define the correct localization of the sensors in height. So basically, this was the purpose of developing a SAP 2000 model. Then it was used the Tremuri, but for Tremuri, of course, we have modeled only the effect of chimneys in our building numerical model. Okay, you have considered all the masses that we have due to the presence of these massive chimneys, and the abacus, the later, of course, the abacus, because you want to study the behavior of chimneys and to get damage parted for different seismic intensities of the chimneys, and this was not possible with the Tremuri. So, and now to illustrate the type of results obtained, the main results for this Manuelino building and just for the other body connect to the the unit 1, I'm going to show very briefly the main results that we obtained. So for the Manuelino building, as you can see, we have the building itself here, and of course, we model taking into account the constraints imposed by the other building. So this is the other building which connected the Manuel building at this part, and this is the kitchen which connects as well the Manuel building. So small parts of these buildings are modeled, the ones necessary to obtain the correct dynamic characteristics of the building and the analysis. And we have considered different types of materials described on the right side of the slide. For the global seismic assessment, take into account the in-plane behavior of the walls. We have performed nonlinear static analysis with Tremury program. So in this slide, it is represented the damage pattern for the ultimate displacement of pushover analysis for the load applied in both directions, X and Y directions. In fact, the distribution of damage of different masonry wall is represented for the near collapse limit state. This extreme situation allows us to identify the most vulnerable structural masonry walls and the type of behavior that we are expecting in shear or bending control behavior. So looking to this, of course, you have significant shear damage and collapse in some of the piers at this intermediate level. So we decide also to just represent the most vulnerable masonry walls as are identified in this slide, just the walls who are the first ones in that building who are going to collapse. And we have also considering the out-of-plane response, the out-of-plane response of the building. The out-of-plane response was evaluated by nonlinear kinematic analysis with Tremury program with the modulo local mechanisms. But given that due to the very good conservation of the palace in general, no cracking state has been acknowledged. Thus, the identification of possible out-of-plane mechanism was based on the geometry of the building and assumptions related to the quality of connections between orthogonal walls and the roof, and between the walls and the floors, the layout of openings, constructive details, and restraints given by the structure as the presence of tie roads. All these have been taken into account to define the mechanism that we have a higher probability of occurrence. So similar type of study have been done to all the other units or bodies that you have divided our palace. Just very quick what we get for the other buildings, bodies 2, 3, and 4 that were connected to that manual in building. So in this slide you have the materials that you have considered for this body. Here again, the damage partner having performed the nonlinear static analysis for both directions. Once again, we have shear problems for the piers at this intermediate level. Here in this slide, it is represent only the most vulnerable walls, and again, the out-of-plane behavior has been considered as well, and we have for the same, taking into account exactly the same factors that I have already mentioned. We have defined different probably mechanism, and you have studied this out-of-plane behavior. So, and to finishing my presentation, just very final comments that I would like to give. Due to the complexity of this cultural heritage building, the seismic assessment poses a strong demand on structural engineering skills and, of course, on the available structural analysis techniques. The procedure herein followed seems capable of providing a reliable seismic assessment of such complex structures. In my point of view, it's a good compromise between computational effort, guarantee a trustworthy assessment. Final, so and some related to this last image, we have in this study had to the beam model the distribution of damage of different masonry walls for the near collapse limit state. These have been implemented in the 3D beam model. In this work, we did not explore the Tremury beam model. This should be explored in the future, and of course, an easy incorporation of these results in beam model as attributes enhance the capabilities of BIM, and of course it will be very helpful decision support within the heritage management framework, and certainly will be it will be very useful for any management team of this type of structures. And that's all. Thank you very much.
So I virtually thank Professor Bento for a very interesting presentation. I think that most of us who were watching their presentation would like to be in her place to work on this very complex, challenging, but really interesting piece of architectural heritage that is definitely something that I think she was very lucky to be involved in, with the resources to work and to do the work properly, and to face these very, very difficult problems in as a structural engineer with some side issues with heritage structures, the need for analyzing complex buildings with uncertain details, uncertain connection with each other, and very highly irregular both in plan and in elevation. I think that now we can move to the next presenter, who is Alessandro Marasca. He's a structural engineer. He's a surely world-famous expert in earthquake engineering in practice, let's say. He had the opportunity of working on very, very big and important projects, and in particular, he recently founded a new company, which is Hopper. He will tell us something about what they do and what they had the opportunity to do in using a pushover analysis of existing masonry structures.
Okay, I think you can hear me. Thank you very much, Andrea.
Welcome.
And I would like to share my screen. Okay. No, sorry. I think now should be correct. Okay.
It was actually better before, because now we are watching the presenter.
Okay. So it's a little bit in delay.
Okay, now it's great.
And I think now you can also see me. Hello.
Perfect. Hello.
Okay, so thank you very much for the well introduction, and I'm very so I saw with very much interest the previous presentation. Very interesting project. So I also prepared a small introduction of myself, but I think Andrea did already a very good work. So I will continue with the following slide. So I would like today to present basically two case studies, and in particular the in-plane performance of two typical buildings under induced earthquake in the Groningen province. And in order to do that, I have divided the presentation in four different steps. So the the first step is basically introducing a little bit the problem. So the induced earthquake due to the gas extraction. The following point is a small introduction about the national code. Of course, the presentation is very tight, so there will not be too much time. And then two basically typical buildings, one terrace house and one detached house. So first of all, for who is not aware, so in the Netherlands and in particular in the Groningen region, there is the biggest gas field in Europe. It was discovered in 1959 and the gas extraction started in 1963. So the gas field is operated by NAM, which is a joint venture between Shell and ExxonMobil. And basically, since 1980, have been recorded thousands of earthquakes until basically the strongest, which was in 2012, with a magnitude of 3.6. From that point, basically a lot of studies started, and basically the gas extraction was reduced from 2014. And basically, step by step, we are arriving to today. So the latest news is that the gas field is going to be closed in 2022. So a small note is basically, as a gas field is basically first a resource and then step by step a problem. So a small introduction about the in-plane backbones and mechanism and equations included in the National Seismic Code. So the first one is the flexural behavior. So the equation is not very dissimilar to the one included also in the Eurocode. The interesting part maybe is the equation about the drift. The equation was developed by the Technical University of Delft in the Netherlands with real experiments. And maybe so you can get sometimes even 2% in-plane drift for in-plane flexural mechanism. The shape of the backbone is very similar to the Eurocode, so to the generally used one in Italy or Eurocode. A little bit difference in the shear behavior. So the bed joint sliding, the peak value you can see from the backbone is derived from the generally known equations, and then there is a post-peak behavior, which is only the frictional part of the equation. Also, an interesting note for this mechanism is the in-plane drift is set for near collapse, because everything here is set for near collapse for 0.75% of the effective height. Maybe another important thing I think is is when to stop the analysis. Generally, a 20% of decay is used. In the Netherlands, in the national code, 50% of the decay, so meaning a reduction of the base shear of half, and this is to basically define the final pushover curve. So a little bit of insight, because I think it's interesting comparing with what is commonly done in the Eurocode, is about the calculation of the demand. So in the Eurocode, as you know, but also in Italy, we generally use the N2 method. Instead, in the Netherlands, it's normal practice to use capacity spectrum method. The capacity spectrum method is basically a method in which the elastic response spectrum should be reduced, accounting for an extra damping. The final damping is basically a sum of the inherent damping, the common 5%, and the hysteretic damping, which is calculated and suggested by the MPR by the equations, and generally, and it cannot be actually bigger than 15%. So one note is that generally all the buildings have easily a 20% decay, sorry, 20% damping. So acceptance criteria, so basically it is an intersection. So the building can be considered passing, let's say, the check if the bilinear, which is derived, of course, from the capacity curve, can intersect the overdamped response spectrum. So let's move quickly to the examples. Who is attending the meeting from the Netherlands will see that this is a very common building in the Netherlands and also in the Groningen province. So this is a terrace house. Terrace house is basically a composition, so a block with more units. It is characterized mainly by large openings in the longitudinal direction in the front and back facade. So we have a very weak direction, the longitudinal, and a very strong direction, which is the transversal. So the load-bearing part is usually the transversal walls. So in this case, you can see there are concrete floors, but you can easily find a version of this building with timber floors. The floors are spanning generally from transversal wall to transversal wall. So another peculiarity of this building is the presence of cavity walls in the perimetral walls, so all around. The reason is, of course, for insulation purpose. The inner leaf usually, not always, but usually is composed by calcium silicate bricks with a thickness of 100 millimeters. Of course, there is a cavity gap with a variable measure, it depends. And then another leaf composed by clay bricks. So the structural part, the load-bearing part, is the internal one, so the inner leaf. So for this reason, generally, the outer leaf is not considered in the analysis because the flexibility of the wall ties, which are these elements connecting inner and outer leaf, is considered, so these elements are considered so flexible that cannot actually engage the outer leaf for the in-plane response. In terms of other walls, so there are some internal walls, 100 millimeters, so very slender. Again, in this case, but is not always the same, the party wall, so the wall dividing two units, is composed by 210 millimeter walls. So what else? So ground floor is PS insulated ground floor, but generally is always a precast floor. The analysis, generally we start the analysis from foundation level. Ground floor is not considered. Maybe I didn't mention this. I think an important point to mention is the floor. So in this case, this is a cast in situ floor, and you can see from this detail that the floor is in between the walls. And in this case, it is assumed that can develop a full rigid diaphragm, basically, because the floor is rigid by itself, but also the connections are completely rigid. I didn't mention the roof. I added a few pictures in the previous slide. The roof is generally timber, and so it is excluded by the analysis. So it is considered as a mass, but not so the well-known non-structural roof of Trimuri. Here is just an example on how to go from 3D model to Trimuri model to Trimuri analytical model, in which, as we just said, there is no roof. Response spectrum can be easily be downloaded from a web tool per street. So some results for this particular building. So the longitudinal direction is governed by flexure because the piers are very, very slender and few of them due to the openings. The capacity is quite large. The spectrum is there is a damping of 20%, creating an intersection. So the check is okay. So the building is okay. So this is the worst combination in X. an interesting aspect of the MPR is that you can account for P delta effects. So basically, when you have not too many piers, you can derive a factor by which you can reduce the capacity or increase the demand, depending. In this case, we reduce the capacity. Completely opposite behavior in the Y direction, basically the strong direction in which the building is reacting mainly in shear due to the squat walls. As we said at the beginning, this is the strong direction, and you can see by the intersection. So the intersection with the elastic spectrum is happening at the elastic range, and also in this direction, basically there are no issues. This is the summary of the 24 combinations. They are all fine, basically. Another interesting aspect to mention is the possibility to take into consideration torsional effects, so meaning reducing the capacity or increasing the demands with a factor to take into consideration the torsional flexibility of the building. And this can be done according to the MPR with a model response analysis. As well known, pushover is not enough to provide basically, or to have an idea about deficiencies and possibly retrofit measure required for a masonry building. So usually when doing this kind of assessment, we do always a model response analysis to check the roof and the timber components, and also, as I said, to calculate the torsional factor, check the existing condition for boundary condition, nonlinear kinematic for out of plane response, check of non-structural element, and check of foundations. The second typology I would like to present is the so-called detached house, in which basically they are isolated buildings, mainly one floor. So they present also a different but still timber roof. Sometimes the roof can be very, very complex. There is no weak and strong direction clearly, so it depends by the configuration of the internal walls. Also for these buildings, we can have cavity walls or solid 100 walls or solid 210 millimeter walls, but always quite slender walls. A challenge of these buildings to model in Trimuri is that sometimes the walls, some of the walls are basically below the level of the ground, of the first floor. So usually we fixed a floor level, and then we play with individual walls in order to match the effective height of the pier, since the final capacity of the buildings will be derived from the effective height. Same as the previous building, we don't model the roof structure. Another peculiarity of these buildings is very often they have timber floor, so flexible floor. So it means that comparing with the previous building, in which a global analysis is correct and possible, for this type of buildings, since redistribution is not guaranteed by the flexible floor, we prefer an assessment wall by wall, in which basically distribution is not taken into account at all. So again, this is shown now to go from a 3D model to a Trimuri model to a Trimuri analytical model, in which we don't have the roof. Response spectrum follow the same as before. Results in this case are presented wall by wall, as we said. This is again one of the worst combination in X direction, in which the outcome is positive. Same for a wall in Y direction. And if we want to have a summary Here, of course, the combination are more, but they are not the combination. It's just that is a wall-by-wall assessment. As you can see also here, basically all the walls are fine. So again, I will not repeat, but basically in order to have an idea about the building, also a number of other analysis and assessment and checks need to be done. So finally, some conclusions to wrap up. So along the years, specific advanced studies and analysis were carried out in order to adapt the approach from Eurocode and New Zealand code to the Dutch buildings for the in-plane assessment. Several tests and research programs were carried out along the years to improve and remove conservatism from the Dutch seismic code. The substantial reduction of gas extraction in the region during the years led to a decrease of the seismic hazard in prevision. And as a result, despite the vulnerability of the buildings and the walls that I highlighted somehow, there is generally no need for retrofit for the in-plane behavior in the vast majority of the cases, basically. So that's it. I would like to give a special thanks to the reseller of Tremuri in the Netherlands, Technosoft, and also to S.T.A to have invited me. Thank you.
Thank you, Alessandro. I think that many of the attending participants, who are almost, we reached, they are floating, but we reached the peak of almost 400, and they will be very interested in your presentation and what you have done using Tremuri in such a challenging case as the Groningen buildings, because really there will, if we start from scratch in analyzing these buildings, we have a number of difficulties that you probably have solved step by step, also with the help of the let's say a special version of the Tremuri program, which was specifically developed for incorporating the NPR requirements and some, let's say, guidelines for that you have also developed during these years that you have been working on these, because of let's say the difficult case of these cavity walls in particular, which is something really let's say different from what we are used to have in other countries, and in particular, okay, in the Netherlands, these induced seismicity condition also, let's say, led to make you work with people who were totally not aware of any let's say experience of earthquake engineering and of earthquake risk in general. So I think that what you have done is really great on this. And this presentation is. I cannot say I'm completely outside of this, because I had also with the youth center a small involvement in this project, but this was they say on the research side, but you were really facing the day-by-day issues of practicing and modeling and finding solutions applicable every day, both for the assessment and for the retrofit of these structures. Thank you again.
Thanks to you.
So I think we can now move to the next presenter. And the next presenter, okay, I'm really happy to introduce, because Alexandre Costa is, first of all, he's a friend. I have to thank him publicly, because I just received some bottles of Porto from him. No, it is true, but I'm joking. No, he's a big expert in existing buildings, in particular what concerns the seismic assessment and retrofit of existing buildings. He has been working on this topic, generally speaking, since many years. I would say now. I met Alexandre when he was a master student, and I've been so lucky to be one of his advisor of the PhD thesis as well. He did his master at the Rhodes School, the famous Rhodes School in Pavia, and then he did his PhD at the equally famous Faculty of Engineering at the University of Porto. So he's one of the founders and partners of this company, which is called NCREP, and I think that Alexandre will show us what they are doing and what they actually have started to do in a systematic way in Portugal. Thank you, Alexandre.
Thank you very much, Andrea, for your nice words. And also, I'd like to thank you for the invitation to be presented in this quite interesting seminar. So, can you hear me perfectly, I hope? And
yes, Alex, we can hear me very well.
Okay, perfect. Can you see my screen also?
Exactly, perfect.
Perfect. Thank you very much. So thank you for your words, Andrea. It is a pleasure to be also a friend and also to face my period of and also my career with yours. I think it was quite interesting to work together in Pavia, and also we are still working together. I hope we can do it also in the future. And also I'd like to thank to S.T.A for this quite interesting seminar. And I hope that with this presentation that is entitled Challenges on the Seismic Assessment and Strengthening of Traditional Masonry Buildings, I will expose and also show briefly what we have been doing in this area in the last years. So my presentation is divided in 4 main points. The first will be the small introduction, then we'll pass also to the presentation of some applied research and developments that we have been doing with Tremuri. And then we'll pass to the main scope of this presentation, that is to describe our methodology and also with the application to 2 case studies, and in the end, some final remarks on this subject. So as Andrea was saying, I'm also founder and partner of MCREP, Consultancy on Rehabilitation of Built Heritage. We are a spin-off from the University of Porto. We are now, this year we are 10 years old. And we are a group of civil engineers with advanced formation in the field of existing constructions with master and PhD degrees. And we have also currently a strong collaboration with laboratories and international research groups. Our main services are 4 that can be divided on the inspection and diagnosis. Also the structural health monitoring, passing through seismic assessment, and in the end, the design of rehabilitation and sustainable projects of different types of constructions. Taking into account a good network that we are doing from research inside Portugal, but also in Spain, Belgium, and in Italy. And indeed, with a very good collaboration that we had been developing with the University of Pavia, we have been doing several works on the characterization of the seismic behavior of traditional masonry buildings in low seismicity regions. We have been working mainly in Porto, and this last year we have been also able to do some work in the city of Liège in Belgium. The approach was similar, so we started from the selection of the most representative building archetypes. From these ones, we develop, and we didn't develop, we calibrate the macro element parameters to simulate the in-plane behavior for this type of buildings, and then we pass through the analysis of typical buildings from these 2 cities. These are 7 models that we used in Porto region, and based on these models, we did linear static assessment with Tremuri, and also from there we analyzed for the buildings on original conditions and then also on retrofitted ones, and then we validate these values, these results with nonlinear dynamic analysis, take into account the flexibility of the diaphragms, and also making use of these models, this is a work that we just finished this year. We passed to the seismic assessment of freestanding elements, as for example, chimneys, parapets at the top of these buildings. So we could also apply nonlinear static assessment and nonlinear dynamic analysis to evaluate the seismic performance of this type of buildings. This has been doing also with a great collaboration with Professor Andrea Penna, make use of Tremuri, and we applied more or less the same approach for these two buildings that are like 2 and 3 story buildings typical of Liège, that can represent more or less 25% of the habitational buildings within the city. So one of our main purposes is to continue developing new tools, or at least increase the knowledge in the area of existing construction, so then we can apply some of these concepts in our daily base designs. In this case, the last point was to derive fragility curves and perform risk analysis for the city of Liège. Concerning this methodology that we applied for the seismic assessment of existing structures. So we starting always from the characterization of structural systems. Of course, you already know this, but at least let's rephrase this again. Then passing through the complete inspection and diagnosis, then passing through the mechanical characterization with non-destructive and semi-destructive tests on masonry, and then also on timber, reinforced concrete, or steel elements, in the case if we have it. And then concerning the calibration mainly of the numerical models, we use also the model identification techniques with ambient vibration tests. And with all this information, we developed our numerical models specifically for the seismic assessment, where Tremuri is our main software concerning masonry structures. With all these elements, we are able to define the best strengthening solutions for each type of building. Let's also make some overview of what is the actual conditions in Portugal. Despite we have been working and we know that Euro Code 8 we use all around Europe, in Portugal it is just as a legal normative since 2019, and since 2019 it is mandatory to perform the seismic vulnerability assessment reports for existing buildings. However, we have been using Tremuri since 2016, and one of the cases that I'm going to show you is the first building that we simulate making use of Tremuri. What are our main challenges? Basically the definition of masonry mechanical properties for seismic assessment, because there is not like a huge database that we can consult. For example, as you have it on the Italian normative, where you have very good indications of the masonry properties. In Portugal, we don't have this type of information. So what usually we do, we make a literature-based definition with a special relevance to the Italian normative. And also we use our database that we are still increasing. We have now almost 50, for example, 50 double flat check tests performed on different type of masonry structures, and our main goal is to continue to increase this database so we can more specifically select the best mechanical properties. So taking into account all these elements and all this information, I'm going to show you these two case studies. The first one, the seismic strengthening of an existing old palace in Odivelas. It is this one on the left. And on the right, I'm going to show you a seismic performance assessment that we made for a building at Lisbon downtown. Both of these buildings are what we can consider it moderate to high seismic hazards from 0.25 to 0.3 G of PGA due to the soil type for these buildings, soil type C for the building on the left, and soil type G for the building on the right. And in Portugal, we must work with both type of earthquakes, so earthquake type 1 and earthquake type 2. Concerning the first case study, so we have a ground floor, first floor, and also the attic that was used during all these years. And this is a building that, with the estimated date of construction on the 18th century, with a total area of construction of 780 square meters. It is a traditional masonry and timber structure, and it was abandoned since 2005. What were the main challenges in this building? Despite being low, it is not a very high building, it's a very low building, but one of the main challenges was to be used as a museum. And we'll see afterwards what were these implications on the design. And also we have flexible diaphragm with timber floors. And one of the major problems of this building was the presence of a severe termite attacks. This is, for example, a wall in the last floor. This is a lightweight timber wall fully attacked with termites. You can see it on the right. So this means that the timber elements were in a bad state of conservation. Let's say that in the end, this was a problem, but the major problem was that at the first floor, so between the ground floor and the attic, the roof, we have all these walls that has mural painting. So this was a major problem in this case study. So these walls were painted, and one of the main purposes of this intervention was to keep the first floor exactly as it was. So the floorboards, walls, also all the wooden elements, and if possible, also the ceiling. And then we decide how to do it, how to analyze it, and then how to strengthen to keep all these elements. So this is just a presentation of the structural configuration. We have at the perimeter walls, there were stone masonry, irregular stone masonry, basically mainly on limestone. We have also some internal walls on masonry, and then we have some more timber framed walls that were also used as load bearing walls. This is for the ground floor. This is the first floor structural plan. You can see the alignments of the timber elements, and here at the bottom we have the structural intervention based on the inspection and diagnosis phase, and considering also the vertical load. So you can see it clearly that this area in the back, it was in the best state of conservation, while these 5 compartments at the front were those ones that had those mural paintings. So the main point was to keep these areas as they were, if possible, of course. So why did we select Tremuri? First was that with this software, we could take into account the nonlinear behavior of the masonry, making use of the nonlinear static procedures that we can analyze this type of buildings. Also, we like it very much because it's a very simple and fast modeling for assessment and design of strength interventions, and it is possible to evaluate the evolution of damages and detect also vulnerable areas. Also, as we have the problem of the diaphragm's flexibility, we could also assess the influence of the diaphragm flexibility with different type of solutions. So what came out from this analysis was that the original structure did not possess sufficient seismic capacity, and in order to improve this type of behavior, we simulate different diaphragm flexibility, where we figure out that improve significantly the global behavior of the building. And then we have also the problem of masonry mechanical properties, that they were not enough to sustain the seismic actions. So we simulate also different type of intervention as wall injections, mainly on the masonry walls, and also reinforced concrete plaster that we didn't want to use it, but we just want to assess the efficiency of this type of intervention. All these improvements were made based on the masonry properties, that the improvements that comes from the Italian code. This is an image for the same displacement for a pushover analysis along the X direction, so along the main facade. We can see here the main facade damage pattern, you can see that we have like some damage concentration here on the edges, some more damages at the bottom, and also some failures of elements along the building. And you can see it that on the strengthening structures, mainly based on the stiffening of the diaphragm, some improvements of the masonry properties, we could have a more spread damages and with not a lot of damage concentration on certain elements. Taking this to account, we have here some images of intervention. So, for example, the application of Syntec anchorage systems at the corners, at the edges, so we could connect perpendicular walls. Also, some improvements of the diaphragm stiffness. How did we do it? So we took into account the existing timber elements that were in the best state of conservation, but we introduced intermediate supports, so we could maintain these elements, so we could keep the floorboards at the upper floors, and making use of horizontal timber trusses, we increased like the stiffness of the diaphragm due to under shear forces, under distortion forces. Also connecting all these elements at the perpendicular walls, we were improving also the connection between horizontal and vertical elements. This is an image at the top of the ground floor, and this is an image at the top of the first floor. So we have a new timber floor for the attic, and we use a double layer of OSB strand boards. So we were improving also the shear stiffness of the diaphragms. Concerning the global behavior and local behavior of masonry, some of the masonry elements, you can see here images from the ground floor, they were reconstructed, making use of timber framed walls. These are some images from the walls, so from the demolished part that was not in a good state of conservation, and they were supposed to be injected, but during the construction works, in the end, it was decided not to go for a museum, but just go for a more common office building, and it was in the end possible not to use injections to improve the seismic behavior. And here's some local reconstruction of also of the timber floors, of all the frontal walls. And now some final images just to figure out what can be done. So we can see here that all these paintings were maintained. These are the original floorboards. The roof, the ceiling was reconstructed. This is the same compartment before and after the intervention. And it came out that with Tremuri we were able to keep the building as it was. Our main purpose is that was to keep the first floor. So the second case study I'd like to show you is a typical building from Lisbon, and it is a 5-story high building, and it was with a possible date of construction in the late of the 19th century, and it has a total area of 6,500 square meters, also with a traditional timber masonry structure. So you can see here on the right, and mainly at the perimeter walls of limestone masonry walls, the inner core also of masonry walls, and then we have some intermediate walls that are load-bearing walls that now we'll see how are they built. So what were the main challenges here? Was the extensive inspection and diagnosis campaign to characterize correctly these masonry elements, so in order to model it correctly. Also the mechanical characterization that we may use with the flat check tests, also some cores, and then we also evaluate the dynamic behavior of the building, making use of ambient vibration tests. And this was a problem because this was a corner building, and this could be a problem that we need to address and to assess with the seismic analysis. The final occupation of the building was to be used as offices. So taking into account all the information, we start doing the work. And one of the first points was that we figure out that these are some images from the late 19th century, and until 1940, the building was just 3-story high. So in the middle of the 20th century, it came up with more 2 stories. Also, another surprise was that the external and the inner core walls, they were built on masonry walls, on masonry, but the internal load-bearing walls were made on timber, mainly timber elements that were supporting all these 5 stories. So what we used was we used 2 numerical models, one finite element model for gravity loads, and also to assess some local or global behavior for lateral loads, but then we used Tremuri for the seismic evaluation of this type of buildings. On the right, you have the model identification, first model of vibration for the 3 models, second mode of vibration for the 3 models, and from this on, we calibrate our numerical models in order to do the seismic assessment. What was used in our Tremuri model was to assume only masonry walls as primary seismic elements, as you can see it here. So these intermediate walls were not introduced due to negligible contribution to the seismic resistance. We have been doing some works in this area, and in the end, all the stiffness and the strength of the masonry is too big to be able to distribute the seismic forces for other vertical elements. So what came out with the linear analysis with the finite element method was to evaluate some local problems, mainly due to vertical loads. For example, this was a large opening at the ground floor. This is from the here in the middle. This is at the inner core, where we have big steel profiles supporting like a 4-story height walls. So we use it mainly for vertical loads. We try to understand what came out concerning horizontal loads, but in the end, Tremuri was fundamental. So we could introduce correctly the overall properties of the building. With Tremuri, we were able, for example, that we were not able with the finite element model, to identify a problem of a soft story mechanism at the front facade and also at the inner core walls, this area over here. Also, it was a big problem due to the not existence of continuity along the heights. We try also to simulate some different solutions of strengthening, but in the end, only shear walls with coupling beams were able to retain some of the seismic forces, and from them keep some seismic forces outside from the masonry walls. So as final remarks, I would say just that indeed, before starting to go for a deep seismic assessment of an existing building, it is quite important to do a complete inspection and diagnosis. And of course, that when we are working with existing masonry buildings, linear behavior is fundamental. And for these purposes, of course, Tremuri comes with a fast and efficient tool for the linear seismic assessment. Just as a final comment, what we have been facing is that for these massive masonry buildings, we have a very difficulties to change the primary seismic system from masonry walls to other type of systems. So what came as a next challenge that is coming in the next few days, next few months, is going to be the modeling, the seismic assessment model for this monastery of Odivelas, and of course, Tremuri will be again our main software. I'll let you also hear with Ana Simões contact, that is a Portugal, the representation in Portugal of Tremuri. If you need something, just contact him. And also, thank you, S.T.A, for this nice seminar. And if you have any question, please just let me know.
I had lost the control of my microphone. So I couldn't tell anything about your very, very interesting presentation. And I think that I did the right choice in skipping many case studies in my presentation, because the presentation you have presented together with Alessandro and Rita so far, but probably the others as well, will be much more interesting and nice than mine. So I think this was a good choice in this sense. Thank you again, because of this clear illustration of what you have done, reasons, results, methods used. That was, I think, very, very interesting. I'm pretty sure that there will be questions for you in the last part of this webinar, when we will have the question time. I really thank you again for sharing your very interesting experience, and also for the good use you did of these tools, because this is also something.
Thank you very much.
So I think that we can now pass to the next presentation, which is a contribution from Greece. This contribution is from George Tsiamtsiakiris, who is a civil engineer, but he's also one of the resellers in Greece of Tremuri. He works for this company ErgoCAD, and he will, in his presentation, is focused on another interesting case study of a two-story masonry building in Kos, in the Kos Island in Greece. There will be a part related to assessment and a part related to interventions.
Good evening, everyone. My name is George Tsiamtsiakiris. I'm a civil engineer, and today I will present you a case of a construction study located in Greece, and more specifically on the island of Kos. Before I begin with my presentation, I would like to make a quick recommendation for our company, ErgoCAD, which is the official distributor of the Tremuri software in Greece and Cyprus. ErgoCAD was founded in 2007, and this day distributes and promotes specialized software solutions in many countries in Europe and also in Australia. In addition to our official website, www.ergocad.eu, we run 5 other websites related to specific software. In 2015, we started our collaboration with S.T.A company in Tremuri, one of the most innovative software for the analysis of structures built in masonry and mixed materials. Since the first moment, we were impressed by the ease of use of pushover analysis and special tools such as verification of local mechanisms. Tremuri quickly became known in Greece and Cyprus, and ErgoCAD was recognized as the best distributor internationally in 2016 and 2017. Today, Tremuri is used in various engineering universities for the preparation of diplomas and dissertations, which you can find on this page. Those who are interested can find an ebook we created for Tremuri, which includes provision from the Eurocodes and the Greek regulation for building made of masonry, named CAD in Greek language, which is under development. On our YouTube channel, named ErgoCAD, you can also find the recording of a 5-hour conference that took place at the 16th European Conference on Earthquake Engineering, organized in Thessaloniki, Greece in June of 2018. The building that I will present you is a 2-story building on the island of Kos, built in 1929, which showed damage after the earthquake that occurred in July of 2017. At the bottom left, you see how the mathematical model appears in Tremuri. In this case, we used almost all the available Tremuri tools you see on the slide. Due to a law that applies to earthquake-affected buildings in Greece, we had to use the linear analysis to subsidize the owner for the damage to the building. In the final control, of course, we used pushover analysis, even comparing the individual scenarios of pushover with each other. First and foremost, we verified the geometry of the whole building and every element, and all the laboratory tests were done to find the type of masonry. From various parts of the building, we discovered that it had 2 layers walls consisting of volcanic rock, marl, limestone, and limestone. These photos are from the building. We can see here that there is an existing tie rod on the walls. And finally, we received as the characteristic compressive strength a value, Fk, of 3.05 megapascal. At the same time, we categorized the damages of each wall based on the categories provided by the Greek regulation for earthquake damaged buildings. On the left, we can see the 4 letters, the 4 categories A, B, C, D, and on the right, the ground floor plan and the first floor plan. In this slide, you can see again the floor plan of the ground floor and the fixing of the damages. The studies were done by Mrs. Halkidou and Mr. Sifonios. Here we see the categories of each damage. The sum of the damages led us to the conclusion that this is a global failure and not a local one. So it was necessary to proceed with a global analysis. As we mentioned earlier, we had to use the linear analysis because the building was built before 1959 and to insert the seismic forces as horizontal loads to the center of mass of every level with the same value. This is the formula we used, where epsilon is taking the value of 0.14 of G and Ni are the vertical loads of each level. For newer buildings, the distribution is different as it's showed here on the right. So we performed the linear analysis and noted the points where the damages appear on the walls. The goal was to then perform the operations on the damaged elements and to check if they are sufficient or if due to operations failures in other elements occur. Let's see the steps of this procedure. First step, we check the existing building before the damages. We get the results and we continue with the second step. Now we have to repair the damaged elements and check in the same time of the remaining undamaged elements. These are the interventions. First, we remove partially the mortar, install injection tubes at a distance of 30 to 70 centimeters with a diamond shape. Then we have the LimePur IZ8 injection, which contains natural hydraulic lime because we couldn't apply mortar based on cement. Then we add facade grout with Kimia Tectoria M10 mortar. And finally, we have the application of Chemisteel Connect and the wall mesh MR system in 2 directions. We have to mention that according to the new Greek regulation for the intervention of masonry buildings, which is named CADET, it is under development as we mentioned earlier, the application of deep pointing from 3 to 5 centimeters increases the compressive strength at about 15 by using this formula, and about 7 when we apply injection grout by using the second formula. In our case, we use both of these interventions plus the wall mesh MR system, and for this reason, we increase compressive strength of the wall and the shear strength at about 15%. In this slide, we can see the materials. We have the Kimia Tectoria M10 mortar, the lime pour, the wall mesh MR, and the Kimi Steel Connect. We also added new brick units and steel bars on the intersection of walls where we had significant damages. Through the next slides, we can see the whole process. The images are not from the real project, but from the brochures of Kimia and S.T.A companies. First, we cut out the mortar from the joints. We drilled the wall and we installed the tubes and fastened them on the wall by using beton fix. And we inject lime pour, which is acceptable for historical monuments. Some days later, we started leveling. We prepared the mortar, we laid down the first layer, and then we make it smooth. We put the mesh and we embedded it. Later, we drill the wall and we insert the connectors and we lock them. Finally, we overlay the connectors and apply the final layer of plaster. During the same second step of analysis, we decided to add a new layer with wooden planks in order to improve the displacement of the first floor. After the analysis, we had some failures on undamaged elements, so then we decided to replace the existing timber floor of the second level with a concrete slab, and we added concrete beams on the external walls. Finally, we applied the reinforcement, putting a vertical and horizontal mesh of rebars of 8 millimeters diameter every 15 centimeters. You can see on the right with the blue color the wall mesh MR application, and with Greek color the reinforcement with steel bars. In addition to linear analysis, we ran a static analysis for the verifications of vertical loads as they are described in Eurocode 6, where all the walls had enough bearing capacity. We can see the results here. We also ran a model analysis in order to determine the node which has the maximum displacement. This could be the control node of the pushover analysis. And because we wanted to find the percentage of the mass which is effective for each mode, and later we checked the walls through a seismic analysis for the out-of-plane bending. As we can see, all the colors were green. That means that all the checks are satisfied. As we explained earlier, for the linear analysis, we took a ground acceleration of 0.14 of g because of the Greek regulation. The real ground acceleration, because of this earthquake, was estimated at about 0.6 to 0.20 of g. We collected this data from the website www.itsac.gr, and for this reason we decided to run additionally some scenarios by using pushover analysis. For the pushover analysis, we took a peak ground acceleration of 0.24 of G, which is the value according to the current seismic zones of Greece. We ran analysis first for the existing building, and as we can see on the diagrams, the A factor, which is the ratio of PGA of each limit state for each pushover analysis, to 0.24 G is over the one, except the damage limitation state for the X direction, which is 0.9. On the opposite, all the factors for the pushover on Y direction are under the one value, as we can see in this diagram. Here we present the results after the applied interventions. We see that all the A factors are over the one, except the damage limitation factor on Y direction here, which remains on a low level. But since the decision of the owner was to check the building for the severed damage state, we didn't go further in analysis. Also, we have to note that the maximum displacement of the existing building was 1.63 in X direction and 98 in Y direction. After the intervention, we had 2.65 and almost 3 in Y direction. Based on the results of another pushover analysis where we used ground acceleration of 0.14 of G, similar to the linear analysis, we can say that the total cost of intervention could be reduced at about 30%, comparing to the conservative results of the linear analysis for the same ground acceleration. It is worthwhile to mention that Tremuri gives a lot of tools to the end user. In this case, for example, we ran pushover analysis for all the main direction and centricities of the 3D model, 24 in total, but we also ran additional analysis for more direction in order to verify how the structure reacts to the direction of the real seismic force. Some other useful tools of Tremuri are presented here. We can compare the pushover curves, the different scenarios of intervention in order to find the most efficient in terms of cost. We can see the stresses under each wall, or we can run pushover analysis for every single wall, assuming that it is isolated from the other elements. We also, in this example, checked how the structure can be responded if we divide it in two parts. The results were obviously better, but the division is not acceptable because of the region where the structure is built. One of the advantages of Tremuri is the tool of local mechanism, which helps us to check every single part of the walls for the out-of-plane behavior. You can see here an example. On the left, there is a failure. For this reason, we inserted some tie rods, or we replaced the existing ones on the structure. You can watch a detailed webinar for local mechanism in Greek language in our YouTube channel. In conclusion, we need to mention that there are some parts of Eurocode 8.3 which lead the engineers to use pushover analysis. These parts are on the opposite direction of the Greek regulation for the damaged masonry buildings, but we hope in the future there will be a common solution for these types of structures. More specifically, in Eurocode 8.3, the application of linear methods has to follow these conditions. The floors possess enough in plane stiffness and sufficiently connected to the perimeter walls. Floors on opposite sides of a common wall have to be at the same height. Walls are continuous along their height, and lateral load-resisting walls are regularly arranged in both of horizontal directions. If you check these images, for example, you can see that the buildings on the right are not valid for the application of linear method. The same in this slide. Non-linear methods should be applied when the conditions are not met. Since all the existing masonry buildings have floors made of timber, it's not possible for the engineers to use linear analysis, and it is something that has to be solved in the future. In this last slide, we can see some of the most important companies in Greece and Cyprus that have already invested in Tremuri.
Okay, I think this presentation was also very interesting, and in particular, it is interesting to compare the different approaches and the different code regulations that still are implemented in different European countries. Besides, we have a common code, which is Eurocode. Then the national regulations can be very, very different. The same applies in particular for the presentation by Alessandro Marasca, was say showing the application of this Dutch code that was actually partly derived from Eurocode, but also with some influence from the New Zealand and US codes. I think we can now move to the next presenter, which is Henning Kirmse from Austria. I think that there will be some other interesting case studies and analysis that he will show us. Thank you, Henning.
Thank you very much. First of all, I feel very honored to be invited also to that event by Ingvar and S.T.A. And I want to switch. Can you hear me? I guess it's fine.
Yes, we can hear you. I can see you.
Okay.
Still not your okay.
Screen must be there now.
We see it as well. Okay, go on.
Yeah. Yeah, because I understood it as an interactive exchange, so I don't want to go so much in detail. I just had the idea to present a little bit how's the situation in Austria, especially in Vienna, what types of buildings we have, what is mostly our task, what we have to do there. So our company, KPPK, is consulting engineers for civil engineering. We are not only doing structural engineering, building services, fire protection, and everything. And so mostly clients want to have the whole field of engineering when they are coming with a project to us. The typical masonry buildings in Vienna, I mean, I'm just talking about 80 or 90%, are mainly built around 1880 until 1920. And they're typical construction parts, arched ceilings, mezzanine above the cellar normally, and in upper stories mostly you have wooden beams and walls, of course, masonry walls. Sometimes there have been changes, but mostly you find buildings like that. And then our planning tasks consists also mostly of typical things: removal of walls, addition of an elevator or parking garage, and of course, last but not least, the attic conversion, which is the most typical thing, and addition of elevator and parking garage is coming mostly together with it, because this is bound together from the authorities, because if you want to build up an attic conversion, it is a must that you have to build an elevator and parking garage also. So that means in that case, you have to take care of all of these parts. The material part is mostly tested in situ tests. Sometimes they're also taking some parts of the bricks and the mortar, but it is mostly done in situ test, and you can see these are more or less the characteristic value I was writing there, which we found here. To typical floor plans, this is the most standard case, you can say, where you have the outside walls. Street wall is one here. Then you have a middle wall and the back wall, you can say, on the garden side or courtyard side. And all these beams, which we have mostly, the wooden beams in the ceilings, are from the outside walls to the inside walls. So that means that walls are the main walls for that buildings. This is the main typical floor plan. And there are slightly some other typical, this is that one. This is like a corner building type, which causes very often here in that corner some problems, in my experience. Next one, which also very often, is the typical two houses with in between the staircase. Then it can be like on the left side, where you have the staircase directly, but then you have a split level between the two houses. And the other possibility is like it is on the right side, where the staircase is rounded, and so you don't have any split level there. So that is what I told before already. The main walls are all the loads going through that main walls. That means, and these are secondary walls in the y direction. Main walls, I can add these typical sizes are around 60 centimeters in the upper stories. They will a little bit less, like 45, except middle wall. Middle wall is, you can say, 60 centimeters from the ground floor to the attic level, because there are also chimneys inside very often. So that secondary walls are the walls to the neighbor on that side, which are mostly 30 centimeter, and in the attic level then only 15. And the staircase walls are also like 30 or 45. And then this special thing, these extra walls, which are rectangular to the outside walls, they are very thin walls. They don't take any loads. They're just for the building there in between. And these walls are mostly the important factor. Then there are some different ground views, you can say. This is a combination of the standard one with a small part on the backside. This is a huge type, two buildings with two staircases, or corner building with a small part on the backside with also 2 staircases. But all these different ground views you will see are similar in wall thickness and ceilings. Yeah, also with sometimes you will find houses with a courtyard inside and the house is going around. And this is a special big one, what is going around and has also a circular corridor here inside. What is going around? This means you have this staircase here, a staircase here, and all is connected with one corridor which is going around. Ceiling constructions. We have also very typical wooden beams. Of course, this is the standard which you find in almost every house. These are typical between 20 to 26 centimeters. Sometimes can be also the height a little bit more, 30, but this is really seldom. This is a very massive one. I just put it here because it was a nice picture. This, I must say, is a building which is a little bit older than what I mentioned before. So that is a very massive ceiling. And then we have that Dippelbaum ceiling. I did not translate that because I was not sure was the what could I find in English. That means you have one wood to the other, and they're connected with solid wooden pegs. So that gives that construction a very solid type. They are found. This is found mostly as the last level above the 3rd story or so, you can say. You will find very often this type of ceiling. Yeah, and then we have also sometimes in the later part of the period, you will find not only wooden beams, you will find steel beams, and between that steel beams, you will have the wooden beams. Steel beams then have a distance 3 meters or something like that. So the wooden beams inside that are a little bit smaller than before. Of course, in vaults and arched ceilings of masonry, this is mostly found in the cellar or above the ground floor. Sometimes in bigger buildings, you will find it also in almost every floor, and typically is the ground of the bathrooms or something like that are mostly built up with that ceilings. Yeah, this is also a cellar type vaults, which is typical to find. And then strengthened construction did mostly done by the composite structure of wooden beams and concrete slab, small concrete slab around 8 centimeters, which gives that ceiling a very stiffness, so that you connect here all walls of the building in that area of that ceiling. Then I must say by the authorities until 2008 or so, there was a standard here regarding the seismic loads, and then from 2008 started the area of the EC8, and in the beginning time it was a very difficult thing with the attic conversion because it was not clear how to do that in a static analysis. And then in 2013 it came the new national annex, and here it was found the possibility. It is similar to the Swiss standard, because all the buildings, they don't have the 100% earthquake resistance. So, or it's really rare to find that. So that means we have to see what's the resistance of the existing building and what's the resisting after the construction. And this is also done before with a reliability analysis. I just try to translate a little bit and put some example. That means you have to calculate a number of persons who are in the building. This is in different categories. Let's say 10 flats, and there are 2.35 persons each flat. And then there's also a time factor, which is in case of the flat is 1. So that means in that building with 10 flats, you have to calculate 23.5 persons. And then you are building up in the attic story 2 flats, let's say, then this will be higher. And this I marked here, there are 4.7 persons more in the building. That means in that standard is saying you have to see what is first the seismic resisting factor, let's say, for example, 40% of the existing building. Then you have a probability of breakdown existing building and the number of persons existing building, which we had here. And then with that curve, which is also like in the Swiss code, you have a correlation between the seismic resistance factor and the probability of a breakdown. And then you're calculating it in that, and then back to the next one, what is the planned situation? And then you have here the number of additional persons again. And with that formula, you get the result, how much you have to strengthen the building. That means your existing building has 40%. With that additional persons you want to, with the flat, put in the building, you have to reach the 44%. So that is mostly the task which has to be done. So that means if I put in one, we have the existing building, the resistance factor, number of additional persons, and a required resistance factor. And then we are calculating the resistance factor. Sorry, I did not translate that. Then we get a resistance factor after changing the building with the additional persons and additional loads from the attic story. And then this must be fulfilled. Then the authority will accept. What I forgot to mention is that here, it is important to know, additional persons is only 50% more than existing in the existing building. So that does not mean you can bring up more than 5 flats in that case extra. Okay, then I'm coming to 2 projects. This is a very typical one, which is now in the authority phase, the permission phase. This is like a typical building. Here you see that existing situation done in Tremuri, and the mesh with the ground view, and we could figure out here the element wall, which was, here comes the building about 43%, 44% of the earthquake. And then the planned situation, the strengthening was the ceiling above the 3rd floor, because that was also of wooden beams, and there will come a composite wooden beams, concrete ceiling, which is connecting all the inside walls then, and can transport the shear forces from one wall to the next one, and we can activate walls like that or like that. And also, of course, there is a lift here in concrete, which will bring also a positive effect. And then we are calculating that the planned situation, and the same comes also, building will same, only loads will be changed, and the lift is coming, and the ceiling. And you will find the important element here, and we could raise up around 10% the seismic resistance. Project 2 is a little bigger one and has a longer history. You can see here a little bit on the photos what was the history. They are built up here antenna, and then now it has to rebuild. So that is also the existing situation you see here. Special is that here in that story there's a big hall, you can say. These rooms are around 7 meters high or so. And then we were again calculating that in the Tremuri. Found there was an existing concrete shaft inside. Found the element. And then here some more strengthening have been done, such as steel frames here in that areas. Ceilings, all ceilings were stiffened with either concrete slabs or composite wooden beams, concrete or solid timber boards on wooden beams. And also new shafts for lifts were built up inside and connected with concrete slabs to the rest of the building. And then it was also calculated again. You see here these lift shafts inside. And again, we got after that the new seismic resistance. Yeah, and some impressions of that building. Here we can see that we're building that massive steel frames. Also some injections in some areas with in the masonry walls have done. Here you can see that the beams we leave inside the wooden beams and strengthen it with other wooden beams, and then above it was coming a solid timber board connected with outside and inside walls. Yeah, there were also done a lot of concrete works because that building had 3 basement floors, which got a garage inside, and then it is the building after all constructions were done, how it is now. So that is more or less on the end. Thank you very much. Thank you very much to S.T.A and Ingwer, which is the distributor of Tremuri here, Austria, Germany, Switzerland, as far as I know. Thank you.
Thanks a lot, Henning. I think that also your presentation was really rich of very interesting information about, in particular, the use of Tremuri for these very large buildings, which you have done a lot of, say, diagnostic and modeling activities. So you have a knowledge of these structures, and you have shown us that they are very, let's say, specific and with some features that are for what I know so far, very specific of this context of the city of Vienna in particular, in Austria, but in particular the city of Vienna, I think. And what I would say is that it is very interesting also to see how such large structures have been analyzed using nonlinear analysis methodology, because actually you have done because it is simple using Tremuri. You simply push a button, but in the end you are performing a nonlinear analysis which can last, say, a few minutes, but actually in this case I think you did a great job. What I would stress in this case and in other cases that once you have an analysis of such a large building, you should, and you probably have done, check the convergence of your analysis. So you can play with some analysis parameters, and you can verify if your solution is, say, robust enough. I mean, in terms of curves and damage you get. Thank you again.
Thank you.
So I think we can now move to the next presenter. The next presenter is from Italy. She's Romina Sisti. Romina is from, actually, she's from Umbria, if I'm not wrong, but she is now working as postdoc at the University of Naples. Romina. Okay. Ciao Romina, welcome. So we cannot hear you so far. Good
evening.
Okay. Yeah. Good evening, Romina. Okay. So I can leave you the floor for your presentation. I don't know exactly what will be the topic of your presentation. I guess it will be about the analysis work that have been done for the city of Camerino. Exactly. Okay.
So.
Okay, we can see your screen. Okay. Okay, we can see your the presenter view instead of
okay. Okay. So.
While Romina is solving this technical issue, I can say that this topic of Camerino is very interesting because the city of Camerino was completely closed after the earthquakes that struck central Italy in 2016-17, and it is really a very relevant work that what so Romina is going to present. Because okay, we can see your presentation.
Okay, thank you.
Okay. Okay.
So
please.
Okay. So I'm going to present our recent work carried out in collaboration with the Italian Inter-University Consortium ReLewis. And in this work, we analyzed the seismic performance of 4 heritage buildings after the 2016 Central Italy earthquakes. And today I'm going to show you one of these, the Palazzo Comunale located in Camerino. Okay, Camerino is a town of about 7,000 inhabitants and is situated on a hilly region of central Italy, and his historic center stands on the top of one of these hills. This graph is taken from the Italian Parametric Earthquake Catalog and depicts the seismic history of Camerino. In particular, it shows the earthquakes that struck the town in the last 1,000 years with an intensity greater than 3, according to the Mercalli-Cancani-Seeberg scale. And it's clear that several strong earthquakes struck the town in its history. And focusing on the last 25 years, Camerino experienced 2 important seismic sequences. In 1997, the Umbria-Marche sequence, and in 2016, the Central Italy seismic sequence. The last seismic sequence struck 4 regions of central Italy between August 2016 and January 2017. And in the figures, the red stars mark the epicenters of the 8 main shocks. The first 2 events at the end of August didn't cause many damages in Camerino, while the 3 events at the end of October damaged many buildings. The maximum value of peak ground acceleration in Camerino occurred during the earthquake of the 30th of October and was equal to 0.16 times the gravity acceleration. And in this shake map is marked by the dark yellow color. Palazzo Comunale is a building in the historic center of Camerino, and before the 2016 earthquakes, it was used as a town hall. It's possible to find this ancient building even in some plans from the 13th century, when it already shows the same square shape and the same internal courtyard that we can observe nowadays. As you can see from the map, Camerino is a part of a masonry complex, and that means it's part of a related group of buildings that were subjected to various transformations over the centuries. And in particular, in the west side of Palazzo Comunale, there is a theater called the Teatro Marchetti that was built in 1728, demolishing pre-existing structures. And Palazzo Comunale is a 3-floor building with an average floor surface of about 1,400 square meters. And the building is characterized by the presence at the first floor of 3 staterooms with the double height, with the Camorcanna boats that are boats made of plaster and a reed straw hanging from the wooden centerings. The presence of these double height rooms cause irregularities in elevation and strongly affect the planned layout of the upper floors, splitting it in 2 portions that don't communicate with each other. Due to the seismic event of 1997, the Palazzo Comunale suffered extensive damage, mainly due to the poor quality of masonry and the lack of wall-to-wall connections. In particular, the activation of the simple overturning of the main facade was the most insignificant damage. And on opposite, the continuous theater was not damaged at all. In order to repair the earthquake damages and improve the seismic behavior of Palazzo Comunale, strengthening measures were designed and realized starting from 1999. In particular, traditional strengthening techniques were adopted. The mechanical characteristics of all existing walls were improved by means of grout injections. The wall irregularities were reduced, walling up the wall niches or hollows. The bending capability of some masonry panels were increased, inserting vertical tie rods. And the original wooden floor or roof were either replaced when too poor or stiffened when too flexible. And finally, the wall-to-wall connections were improved, inserting several tie rods. The 2016 event represented an opportunity to evaluate the effectiveness of the strengthening solution adopted in 1999. And for that reason, we carried out in situ surveys to detect the damage caused by the recent earthquake. And here you can see an example of one of the buildings plans where we represented with different red symbols the different type of damage, and we put blue marks where we took pictures to provide documentary evidence of the damage. I will show you a brief overview of the main damages. We observed some cracks on the interface between the main facade and the vaults at the ground and first floors, but not damage was observed at the top floor. So we can rule out the possibility that the main facade or a central portion of it was subjected to a vertical overturning, while the vertical arch mechanism may have been activated. Widespread millimetric cracks were observed on the load-bearing walls, whereas only few cracks involved the entire thickness of the wall. In these cases, there are often discontinuities in the masonry layout, like the one you can see in these pictures, that may have facilitated the crack development. Severe damages occurred in the non-structural components in the stucco decorations. Sometimes inadequate construction details cause local damages, as in the case of the connection of these wooden truss and the masonry underneath it. And the most severe damage was observed in the theater, where the external layer of the masonry gable crumbled due to the poor quality of the masonry and caused the partial collapse of the portion of the underlying roof structures. In addition, the earthquake caused disarrangement of the theater's roof covering, and unfortunately, the necessary countermeasures were realized only after 3 years, and so the rainwater penetration led to the collapse of the camorcanna vaults of in the gallery. So, as mentioned before, Palazzo Comunale is a part of a masonry complex, and given the historical evolution of the complex and the structural morphology of the structural units that made it up, we decided to split the complex in 4 structural units having homogeneous characteristics, and model each unit individually rather than considering the numerical analysis of the entire complex. So a 3D macro elements model has been used in order to simulate the seismic response and the damage pattern of the Palazzo Comunale, and the structural interaction with neighboring structural units were considered by the introduction of corresponding loading and boundary condition. 2 different models were created to assess the seismic response of Palazzo Comunale before the renovation work and after the renovation work. We then compare the results obtained from these two models with the damage observed after the 1997 and the 2016 earthquakes, respectively. The mechanical properties of masonry wall were assumed according to the values provided by the Italian code for the masonry typologies detected in the Palazzo Comunale, while other material properties and structural characteristics values were borrowed from the original project documents. Okay, so to investigate the global response of the building, simplified displacement-based procedure using a nonlinear static analysis was performed, and the model was loaded with a distribution of in-plane actions, which were monotonically increased to simulate the effects of the inertia forces. And two systems of lateral forces distributions were applied, not simultaneously. In particular, the first distribution was proportional to the displacement of the corresponding first model shape, and was chosen since it was representative of the behavior of the structures in its original undamaged configurations. And the second distribution was proportional to the inertia masses, and it was more representative of the behavior of the structure at collapse. And as control node, it was decided to adopt the average displacement of the nodes at the roof level. And to express in a concise way the results of the analysis related to the two models, I have reported only the values of the minimum seismic safety index, the alpha parameter, defined as the ratio between the maximum value of seismic acceleration corresponding to the attainment of the life safety performance level and the expected maximum acceleration prescribed by the Italian code. Before renovation works, Palazzo Comunale exhibits a very poor performance with a seismic safety index equal to 0.35 as a result of sheer progressive failure of the piers. And the 1999 renovation allowed to increase the safety index and mainly achieved thanks to the improvement of masonry quality and the reduction of irregularities. And in both cases, the damage pattern simulated by the software are in good agreement with the damage pattern surveyed after the seismic events, and showing that the software is a valid tool for the safety assessment of the existing masonry buildings. And regarding the results of the analysis related to Model 2 that consider the Palazzo Comunale after the renovation work, we can note that the seismic capacity corresponding to the attainment of life safety performance level is equal to 1.41, and the value is 65% of the design value prescribed by the Italian code. And the achievement of a capacity equal to 65% of the design actions was exactly the design criterion adopted in the project. So we can deduce that the results obtained with modern analysis do not diverge from those obtained with the calculation methods available at the beginning of this century. And we can also compare the seismic capacity with the maximum value of peak ground acceleration occurred during the 2016 seismic sequence. As you can see, these two values are very similar. In fact, the damage observed after the earthquake perfectly coincide with the definition of the life safety performance level. And as you know, the pushover analysis just presented takes into account only the in-plane behavior of the masonry panel. And it is necessary to analyze the out-of-plane response of the walls and verify the activation of local collapse mechanisms. And for this purpose, a macro element approach based on the theorems of limit analysis was used. And each mechanism involves only single masonry panel or an isolated portion of the buildings that are considered structurally independent from the rest of the building and are modeled as a set of rigid blocks connected with hinges. And these figures show the seven mechanisms analyzed, and which were defined according to the construction details, and construction details such as existing wall-to-wall connections or wall-to-floor connections, or structural discontinuities. And the table shows the results of the analysis and reports for each mechanism the seismic capacity for the life safety performance level and the related safety index. And as you can see, before renovation, many mechanisms were characterized by a safety index lower than 1, while the introduction of many steel tie rods allowed to prevent the activation of all mechanisms considered. And that demonstrates the effectiveness of this type of strengthening intervention in countering out-of-plane behavior. So, in conclusion, the damage analysis of Palazzo Comunale and Teatro Marchetti reveal the importance of properly improving the masonry quality in order to avoid the crumbling of some wall panels, the critical role played by construction details to prevent local damages, and the importance of ensuring a faster realization of the short-term countermeasures. And the 2016 earthquake caused less severe damages in Palazzo Comunale compared to the ones due to the 1997 event, showing that in case of extensive intervention on both vertical and horizontal structures, reduced damage level can be achieved even for heritage and irregular buildings like the one we analyzed. And in fact, the renovation work significantly increased the seismic capacity of the Palazzo Comunale, and as shown by the results of the numerical analysis that are in good agreement with the damage observed after the earthquakes. So Thank you for your attention, and thank you, S.T.A for to invite me in this meeting.
Really, thank you, Romina, because I think your presentation was very, very interesting, as the previous were, but in particular in your case, I think you have stressed many aspects that deal with the confidence we can have with these tools when we apply them to the assessment of existing structures. Another topic that you have stressed, and I think it is common somehow to what was introduced by Henning Kirmse, was that also in your case you had the possibility of assessing the partial compliance provided by the intervention performed after the event of 1997, and in this case we have unfortunately the test of those interventions. So also from this point of view, this presentation was very, very interesting. Now I have to move to the next presentation, which is mine, and I hope will not be too much boring, because we are a little late. I try to stay in 20 minutes or so, say. Okay, I hope you can see my screen. Okay, and the title is quite general. The topic is what we have seen so far, so the assessment of existing buildings using pushover analysis. And existing masonry buildings are those that better suit this approach of nonlinear analysis applied to the assessment of their capacity, because they are intrinsically nonlinear. Their behavior is nonlinear since the beginning, since the early deformations. And we have stressed also in this last presentation of Romina, but in the previous as well, I can remember those of Rita, Bento, of Alexandre Costa, Alessandro Marasca, and the others. This issue of this local mechanism that can be prevented using suitable devices that connect perpendicular walls and walls to floors to contrast this mechanism and allow the activation of a global response, a global behavior, which is governed by the wall in plane response, and then which is also ruled by this in plane stiffness of the diaphragms. I will start with this say video, in which you can see two stages of one recent test that we have performed in Pavia on this reduced scale two building aggregate. Measure building aggregate is representative. It was meant to be representative of a situation typical of a historic center in Switzerland, in the city of Basel. And you can see from the video on your left that the local mechanism was actually activated in this part with the starting of overturning of this part. But then once we had activated wall to diaphragm connections and these tie rods, then we could move on and continue to a much higher level of acceleration, preventing this mechanism and then activating I would say activating a lot the in-plane damage and the in-plane response, and then the in-plane damage of the walls parallel to the shaking direction. This was a stone masonry building. The use of pushover analysis is, pushover is a nonlinear static analysis, which allows carrying static analysis. So we accept that in the calculation of the displacement demand, we will use some simplified formulae, but we can identify the evolution of strength with the lateral deformation, and we can identify potential mechanisms and fragile elements. We can predict the localization of deformation demand in specific elements, and we can then try to target our interventions to improve all these characteristics. So we need some tools to do this kind of analysis, and we can apply this analysis both to the global response of buildings, or to the response of specific walls if the stiffness of floors is not allowing global box type behavior. The idea is that we apply a system of horizontal forces to a structure which can be also transformed into an equivalent single degree of freedom system. We use this a bilinear approximation typically, which is then the basis for computing not only the capacity but also the demand, in the sense that we can use the bilinear formula parameters to compute the displacement demand. In this case, you see what is reported in Eurocode 8, which is the famous formula by Professor Pfeiffer. What is also relevant is that pushover analysis provides, I would say, the evolution of capacity with increased lateral displacement, but also it allows to check the spread of damage and the peak of damage for increasing displacement. In this sense, it is widely recognized that displacement, lateral displacement in particular, is a good measure of damage, is a good proxy of damage. So we can easily use this global displacement as a measure of the damage levels for different limit states. And in particular, you can see in this case, you can identify these points on the capacity curve, identifying the different limit states, which can be operational, slight, moderate, or severe, or near collapse limit states, depending on the codes and depending on definitions that the code provide with this for these damage states. I was saying before that we need a tool, a computational model for running pushover analysis of masonry structures. There are many characteristics that you can see are listed here that this tool should fulfill, and so they have to comply with all the failure modes and of all structural members that are included in the model, which can be included in the model, and these failure modes are associated with strength criteria that are depending on the different codes. So this from this point, but also not only from this point, tools need to be flexible enough itself, so to accommodate for different code regulations and code settings that can be different. It has to satisfy local and global equilibrium. It looks an obvious statement, this one, but I can guarantee it is not. I'm not talking about Tremuri, obviously, but there are other codes or other approaches which are not respecting equilibrium. It has to provide a reasonable compromise between accuracy, simplicity of use, and the capability of interpretation of the result. it also allows to identify the damage thresholds starting from the damage you observe in the different members, and then you can report as a global condition for the model. This is a picture I prepared a number of years ago. I always like it because it is somehow clarifying what is a pushover analysis or a pullover analysis, because it is a system of forces that are applied to a system of, in general, generally speaking, horizontal forces that are applied to a structure, to the nodes of a structure, and they are increased until the lateral capacity increases when we increase the lateral displacement. But then when this car is continuing to move, to increase the lateral displacement, it can occur. It normally occurs that at a certain point the strength capacity is reached, and then if we increase the displacement, the lateral strength decreases. And it is very important that you also follow that softening branch of the curve, so that we follow the curve, the evolution of the lateral capacity once the lateral strength is no more increasing, but can increase with the increase in displacement. It is helpful to identify properly limit states, but it is also important to consider an important part of the structural capacity before collapse. In terms of results of a pushover analysis, we have the evolution of the base shear, which is the sum of all these forces that are applied, and it is expressed as a function of one displacement, which can be a real displacement, typically the displacement of one node at the top story, or can be a virtual displacement, which can be, for instance, a combination of displacement at the given story. Can be usually the top one, in case of very flexible diaphragms, for instance. Starting from these analysis, we get the capacity curve, and then the capacity curve can be transformed. And after this transformation, which in the end results in the capacity curve in a spatial diagram with spectral acceleration, spectral displacement, the curve can be approximated by a bilinear curve, which is helpful to compute the displacement demand. The different code provide different solutions for this last step, and we will see that in some cases they are very different and can provide different results. And the result that Alessandro Marasca was showing about the Netherlands are actually related to one of these cases in which the original version of this Dutch code refer to a very conservative prediction of displacement demand. The equivalent frame approach is something that we have developed following, first of all, observation. And if you watch at the damage after the main earthquakes in areas where we have masonry buildings, the last relevant one is the one in Croatia, we can notice that damage is typically concentrated in specific elements. In particular, you can see this damage concentration in piers, in some cases in spandrels, or a mix of damage in piers and spandrels. But these elements are those where typically we have damage concentration. And this allows to idealize the lateral in-plane behavior of a wall with openings as the one of an equivalent frame structure. a structure with vertical elements which are coinciding with the piers, horizontal elements which are typically spandrel beams or other beams that can be present, for instance, concrete beams, or concrete beams representing the out-of-plane stiffness of floors. So we have these mechanisms which are somehow reported in some codes. For instance, some codes in the US which divide this behavior in this soft story mechanism or pier mechanism and this spandrel mechanism. We know that in reality, and in particular in the case of irregular buildings, we typically have a mix of damage which occurs both in piers and in spandrels. And this is also the result of observation, but this is also the result of experimental and numerical evidence, as you can see from the figures on the right. The identification of an equivalent frame model from the geometry of a facade can be let's say almost automatic and trivial operation, or can be an operation which needs the specification of clear steps. In particular, you can see from this plot what is the let's say the rationale followed in Tremuri for this identification. You first identify spandrels, then piers, and then the remaining parts are assumed to be the rigid nodes, the rigid portion of masonry which are connected with the nodes of the frame, which is represented in the figure on the right here. You can see here, and this is somehow simple, very simple in the case of regularly distributed openings. Even if when you are close to the ends of the wall, then you may need to use some rules that increase the effective height of these piers, and these also can be dependent on the type of lintels you have in above your windows or your wall or your doors, because if you have lintels that are very well connected and deeply connected into the piers, you cannot have a crack starting from this point, but then you tend to have a lateral pier height which is the same of the neighbor opening. In case of irregularly distributed openings, then you can still manage to identify an equivalent frame topology. For instance, in this case, you can see that we have a misaligned window with respect to the door at the lower story. In this case, it is missing the window, so we have 3 piers at the in the first story and 2 piers at the second story. So it is a very, say, irregular condition that we can manage to continue analyzing in an equivalent frame approach with some, say, effort. But it is completely automatic now in Tremuri, and you have used many times, and we have seen the application of these principles also in the case of many of the presentations that we could watch before. All the main failure mechanisms and associated strength criteria need to be implemented in these models. So we have to consider the potential occurrence of bending, rocking with the toe crashing, diagonal shear, diagonal tension shear mechanisms, and shear sliding with horizontal or stepped cracks, which can be also ruled by the cracking occurring at the two extremes of the pier. So the response, the lateral response of the piers can be very simplified, but in the model you have to properly introduce all these criteria, which interact with each other, and the common aspect of all these criteria, which is a typical feature of masonry elements, but not only masonry elements, is that the lateral strength is strongly depending on the applied vertical load, and so we can have different behavior and different governing failure modes and then strength criteria depending on the level of axial force acting on the pier. And this is an example of what happens in, for instance, one pier of one building, and the model need to be able to reproduce this kind of effect. So when we push this wall from left to right, then we have a variation of the axial forces. So we typically have an increase of the forces on this side and the decrease on this side. So when we are in this part of the diagram, of the interaction diagram between the axial force and shear force, we see that we are governed by this line, which is associated with, in this case, with the diagonal cracking. And if you look at what happens in the other piers, the situation is different. And if we push this wall from right to left, these piers becomes appear with a lower axial force, and the governing criteria changes, and then so we need a criterion in which the piers is able to account for this effect and consider it in the mechanism that is activated and the displacement capacity, which is associated with the different mechanisms. Here you see an example of a picture that I took casually after the Emilia 2012 event. You see these cracks in this wall, but looking at these cracks, you can identify that some of them are associated with bending rocking, and you see this. There is an horizontal crack here, a diagonal crack here, and this here in this pier, you can see when the inertial forces act from left to right was corresponding to a shear failure. But the contrary happens when the forces act in the other direction, and in earthquake loading this always happens, and then you can see that there are different effective height, but also different failure modes depending on this on the pushing direction. The other important aspect that need to be covered by your tool is the capability of analyzing floor diaphragms considering their actual stiffness. And this is a relevant aspect because this in-plane stiffness of the diaphragm governs the lateral spread of forces and sharing of forces, of horizontal forces among walls in a pushover or in a dynamic analysis. The membrane model, which is implemented in Tremuri, is governed by a few parameters, which can be, let's say, obtained automatically from homogenization in the simple cases, or can be user-defined if we consider, for instance, more refined models for the in-plane stiffness of timber diaphragms, considering the effect of the nail stiffness, or you can use, say, codified approaches, still analytical in the case of the New Zealand code, or say more, say, rough but practical in the case of the US codes. What you see in this plot instead is the same application, which is a little false, but again still applicable in the case of walls. We see that different walls can be associated with an equivalent membrane with nonlinear characteristics. What is still missing, we hope we will be able to introduce in the future version, is also some displacement or deformation capacity to be associated with this kind of equivalent diaphragm. Because in the case of timber diaphragm, of course, we have a nonlinear behavior, but it is typically associated with the larger in-plane displacement. In the case of walls, we can have a fragility of these elements when they are subject to in-plane distortion. The other thing is that in case of very flexible diaphragm, the model allows to perform analysis of single walls, and it is generally correct in the sense that if wall-to-diaphragm and wall-to-wall connections are effective, then we can assume that out-of-plane displacements are prevented. We saw it in the video at the beginning of this presentation, but still we cannot count on any coupling effect of the floors in transmitting forces from one wall to the other. So we can work on this kind of let's say substructures which are the in-plane analysis of walls. But when we do this, we should also account to properly computation of tributary vertical loads and masses, in particular inertial masses that need to be properly evaluated in the case of in-plane single wall analysis. The tie effect of floors, because if floors are connected, they maybe are not providing sufficient shear stiffness, which allows to couple the displacement of different walls, but it can couple the displacement of the different nodes of the considered wall at this at the same level, and it should be also accounted for the tie for the flange effect of portion of the perpendicular walls that can transform these masonry portion in collaborating portions if the connection is suitable. This is an application to a building in Basel, in which we try to consider the effect of different interventions on the in-plane stiffness of floors using the Tremuri program. This is the building. As you can see, in my case study is not as well and appealing as the ones that were presented by the previous speakers, but the idea is to compare the model with very flexible diaphragms. So basically, the initial condition then moderately flexible floors, when we have some stiffening effect of double layer matchboard planks and pavements. Then we have an intermediate case of stiffening diaphragms with say multi-layer spruce plywood panels, so some timber-based interventions, and these almost infinitely rigid floors obtained by applying a collaborating RC slab stiff enough, as in some of the interventions presented in, for instance, those about the Vienna buildings. What you see is that model analysis is providing some results in which for very flexible diaphragms, we typically have independent modes for the different walls, whereas for the rigid diaphragms, we tend to have a global response, and this is also clearly checked in the percentage of participating masses, which is 46% in the flexible diaphragm case, and goes up almost to 90% in the rigid diaphragm case. And these are the curves, and you can see that there is a significant increase in terms of lateral strength when we move from the flexible diaphragm to the rigid one, or at least stiff ones, which is a demonstration that in this case we have a collaboration in between the different walls, which is enforced by the presence of these stiff elements. These are some results from nonlinear dynamic analysis which were performed on the same buildings. I will go quickly on this, but what is interesting is that in terms of comparison between pushover and nonlinear dynamic analysis in terms of displacement shapes, then we see that even in the case of quite flexible diaphragms, in this case at least, the approximation of the displacement or the deflected shape is quite good in case of a pushover analysis performed on a large building like this, instead of performing the analysis on the single walls separately. The point is that not only the displacement shape, but also the displacement demand is say approximately well captured, but in some cases, depending on the load pattern adopted for the pushover analysis, we have better or worse approximation. And this say leads to the last point of this presentation, which is related to the approximation we have intrinsically in the use of nonlinear pushover and nonlinear static analysis, which is the computation of the displacement demand. As I was mentioning before, when we use a simplification like this, we need to use either an overdamping approach, which is the one embedded in the capacity spectrum method, or we can use inelastic spectra, which have a spectral reduction accounting for the activity. This is a comparison specific for the Dutch code, which allows the use of the capacity spectrum method. And you can see that the conservatism of this code can be clearly seen from this thick black line, in which we see that the prediction is systematically the median prediction is systematically larger than the one obtained from nonlinear time history analysis, which could be okay, apart from the fact that the scatter of these results is huge. So when we compare nonlinear static and nonlinear dynamic analysis, we can see that there is a significant scatter using this procedure. And this is something that we can also observe, in particular the scatter issue, for the improved formulation, which is presented. There is an error here. This is not the NPR, this is the FEMA, is the US code presenting the same, say, theoretically the same approach with some improved coefficients, and in particular with an improved relation in between the spectral reduction factor and ductility. So in the end, there is this use of overdamped spectra, but in the end, this damping is derived from ductility, and this is something that in the end probably goes in the direction of using other formulations which directly make use of ductility for the reduction of the displacement, so for the increase of the displacement demand by correcting the ductility demand. And this is the formulation which is provided in Eurocode 8, which derives from the FIFAR proposal. And this is a more recent proposal we have been working on from, let's say, using Tremuri as a, say, nonlinear analysis tool for analyzing a number of systems, also characterized by short period structure, which is the typical condition of masonry buildings. And in this case, we can see that we can correct this trend, which is again conservative for the lower displacement demand levels, but that becomes unconservative in the higher displacement and ductility demand, where it should be more. This is the result of the modified N2 method, and in particular, this is what happens in the case of short period structures. You can see that there is a black line which is not exactly aligned with the bisectors of this sector of this diagram, which should be the ideal case. It is still conservative, but not that scattered as is in the previous case. And this is the comparison again in the case of natural or induced seismicity, and you see that the results are basically the same, at least up to an activity level of 4. Then we can notice a small deviation from the bisector. This is the plot we have seen before. So I thank you for your kind attention. I hope also this final presentation, which was not as nice as the previous one, but I think it has been quite, say, interesting to have something different at the end. So I think that we can consider that after almost 3 hours and a half, we have provided some information. Surely we had the opportunity of watching very different cases, very interesting cases, palaces, marvelous opportunities of research and application, to work on very different heritage structures, ordinary buildings, but with very extraordinary details, as the one of Groningen. The characteristics of this important part of the building stock in Vienna, the specific case of the building in the Kos Island, in which we could see not only the application of the building, but the complex application of the code in that case to the building, to the assessment and retrofit of the building. The extraordinary case of the Sintra Palace, and the very nice applications both to Camerino and to the several cases presented by NCREP from Alexandre Costa. So I thank you all the audience for resisting until this time, and all the speakers for their very, very interesting presentations. Thank you. I think then we can now close the session, and goodbye.
Thank you very much.
Thank you. Bye-bye.
Thank you.
Bye.